And yes, I do music. So that is one of my big hobbies. I occasionally write music, original music, or I remix music from video games that you probably never played because they were for the Game Boy Advance or something like that. Um, so that was what I did during a lot of COVID. Let's go ahead and start a new whiteboard. So today we are going to go over a bit of math, as I mentioned. I'm just going to jump right into it so that we have plenty of time. So your answers so let's go over number 3 and 4. Question 3 says, hey, we've got a t of n over here, and that is equal to, and it's 1 plus 2 plus 3 plus dot, 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 all the way to n, right? And when you look at that, based off the rules I give you, your instinct is to say, okay, so the big of O is going to be O of n. But in reality, that's not the case, actually. And this is probably, of the ones that are on the front page, this one is actually the most important because it shows up all the time. It shows up anytime we're doing when you need to compare one thing to everything else in the list. And when you do that comparison, generally, once you compare one thing to everything else in the list, you can kind of remove that from the consideration from from the rest of the passes that you have to do. So you can set it to the side, and then you say, of the remaining items, I choose one, and I compare it to all the rest. And then of the remaining items, I choose one and compare it all to the rest. Right? So it gets progressively smaller and smaller. For example, let's go over one of the easiest sorting algorithms there is, selection sort. Selection sort basically says here's a 7, here's a 2, here's an 8, here's a 9, and here's a 1. What I'm going to do is I'm going to start at the beginning and I'm going to try to figure out what goes here. So I'm going to look for I'm going to select the smallest item and put it there. That's why it's called selection sort. So I'm going to go and say, so 7's the lowest I found now, 2 is the lowest I found now, 8 is bigger than 2, so it's not the lowest, 9 is bigger than 2, 1 is smaller than 2, so that is the lowest. So now what I'm going to do is I'm going to swap 1 with and 7. I'm going to select 1, put it where set in the right place. 7's got to move out of the way somewhere, so I just put it where 1 was. And so now that's done. Now for this spot, I'm going to find the smallest thing. So 2, 8, 9, 7. Okay, 2 is the smallest, it just stays still. Then 8, 9, 7. Okay, so we're going to move 7 here. We are going to move 7 here instead and put 8. 8, 7, 8. There we go, and so on and so forth. As we do this, we needed to compare 5. We needed to look at 5 numbers for this spot. Then we looked at 4 numbers. Then we looked at 3 numbers, and then 2 numbers, and then 1 number, right? So how many comparisons? 5. I'm fudging the numbers a bit here because technically you're doing 4 comparisons, so I'm just going to explain it like this. You looked at 5 numbers, then 4 numbers, then 3 numbers, then 2 numbers, right? This is the same pattern we're looking at for above. So this shows up all the time. If you did your isUnique method by saying, hey, I'm going to start at int I is equal to 0, but then your inner loop went int j is equal to I plus 1, you did this pattern. So the big O for this is, okay, I don't want to select more options. I want to select the hand so I can go here. The answer for this is actually O of n squared. Now let's go ahead. So now computer science is math adjacent, so I'd be remiss in not proving this. But this particular series, first off, is something special. It's called the triangular number series. Named so because we can put our numbers in the form of a triangle. Like here's 1. So this is 2, 3, 4, and we would call this in the mathematical triangular number series. This would be called T4 because you have 4 layers, and so that would be 1 plus 2 plus 3 plus 4, which is 10. So, it follows this formula. The formula being big scary sigma symbol, right? To say, hey, I is equal to 1, all the way to n for I, which is just which is a more condensed yet scary way to write the equation I had. 1 plus 2 plus 3 all the way to n, is equal to, and the formula is n times n plus 1 over 2. So what this is saying is that this formula, 1 plus 2 plus 3, dot, 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 all the way to plus n, is equal to that, which is, so if we multiply this out, it becomes n squared plus n over 2. So that's why we end up with big O of n. So how is this the case? So I'm going to prove this both mathematically and I'm going to prove it intuitively because, again, I know I have a bunch of people in IST. But the reason I do this is because this is something you hopefully learned during Calculus 2. Not everybody I don't think IST has to take Calc 2 anymore. So for those of you who are taking Calc 2, consider this a freebie because this almost always shows up either in the exam or in the homework. And if this doesn't show up on the exam, then the 1 squared plus 2 squared plus 3 squared does show up on the exam. And that has a similar formula, and you prove it a very similar way, which is a proof we call proof by induction. And this is relevant because it's very similar to how we prove things are correct recursively. Proof by induction basically says we are going to try to prove 1 plus 2 dot, 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 plus n minus 1, and I'm just doing n minus 1 there, plus n is equal to n over n, 1 times n plus 1 over 2. All right? So we want to prove this. Proof by induction takes 2 steps. The first step is what we call proving the base case. And this is very important in recursion. We basically say, we have something in recursion, as you'll see, called a base case, where basically say the recursive case is so simple we instantly know the answer. It also happens to be the case that when we do recursion, we want to basically have everything converge to. In induction, the base case is where we start at. And basically we're saying this is a simple starting point that we can just look at and just kind of know the answer. So what we're going to do is we choose a starting point. Now because this starts from 1 plus 2 plus 3 all the way to n, and it starts at 1, we're going to prove this for n. We're going to set n equal to 1 and prove it for 1. Okay? So this is going to be possibly the easiest thing ever, right? 1 all the way to n is just simply 1 on this side, right? And then we just simply plug in 1 on the other side. So 1 plus 1 over 2. And believe it or not, a lot of times math on your exams is going to be this easy, simply because your professors don't like to do so much work. It's hilarious the number of times that the answer for a physics problem or a math problem was 1, 1/2, or 0, or negative 1/2, or negative 1. Right? So if you're stuck and you need a metagame, that's how you metagame. Anyway, so we can simply simplify this. The 1 doesn't matter anymore over here, so this is 1 plus 1 over 2, which is just simply 2 over 2, which is 1. 1 is equal to 1. Done. Okay, so we've proven it for a base case. We showed that it worked at the beginning of this. Now here's the really weird and funky part. We're going to set, and we're going to assume, that it works for k. We're going to assume that that the formula works up to some number k. Okay? Prove that if k, then it's true for k plus 1. So what does that mean? We're trying to show that basically this formula will work for some, if we're going to, let me rewrite that slightly. We're going to show then n equals k plus 1 is true, basically. I'm not doing it with the formal mathematical kind of style. I don't have time to try to think about how that's supposed to look. I'm just writing this down as I'm writing my stuff. We're going to show that we're going to assume that it works for some number, and then we're going to say if it worked for that number, it's going to work for the next number. And we're going to just prove that abstractly. Why? Well, we've already proved that it works for 1. And so if we can prove this entire block says if it works for some number, it's going to work for the next number, then we can say, well, since we proved this, since it worked for 1, we know it's going to work for 2. And if it worked for 2, we know it's going to work for 3. And if it worked for 3, we know it's going to work for 4. And it kind of just dominoes. This is proof by induction. Basically saying it worked for a base case, and then we generalize it out saying, hey, if we assume that this case is true, then for the next case it's going to work. what that involves is basically rewriting the equation so that we replace all the n's with k plus 1, okay, and then proving it. Okay, so 1 plus 2 dot 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 plus, and then we had n minus 1, which would be k plus 1 minus 1, so I'm just going to write k, right? Plus, and then replace the n in the previous equation with k plus 1. Make sense? Let's go ahead and work on that. M k plus 1. All right? And now on the other side of the formula, we replace all the n's with k plus 1s. All right? So it was n times n plus 1 over 2. So the first n gets replaced by k plus 1. Second n gets replaced by k plus 1. And I'm not going to bother simplifying at the moment. Okay, but notice that basically anytime you see the k plus 1 in parentheses, that's where an n used to be, right? So we just have to prove those two sides are exactly the same. So to point out the obvious, the big issue is this, right? This dot 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 thing. So this is where our making assumptions comes into the rescue, okay? Long story short, we have assumed that 1 plus 2, that this works for k, right? We assumed that the formula works for k. So if so, we can just kind of look at this by itself and say, well, we assumed it worked for k, so we can just simply translate it using the formula that we are assuming is to be true. So we're going to simply say, hey, that is going to be k times k plus 1 over 2 plus k plus 1, right? So all I did was translate this bit, right, into the formula that we're assuming is true. And then we say, let's go ahead and just clean this up a bit. It's equal to, and then the same side, I'm not going to bother rewriting it, dot, 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 right? Okay, it's equal to the same thing. So now now we don't have dot, dot, dots anymore, so we can manipulate this, right? Now, on this side, on the right side, everything's over on a fraction over 2. So let's go ahead and emulate that on the left side, okay? So let's go ahead and emulate that. We are going to do so plus, and then we're going to go ahead and add 2 over, come on, 2, right, which is just a fancy way of multiplying by 1, right? But now everything's over 2, so I can just simply rewrite this, okay, as everything over 2. So 2, we've got k times k plus 1 plus 2 times k plus 1. So let's see. We've got that. And now to get it working, what we do is we actually do some weird manipulation. We pull out a common factor. And typically when we do that, we're pulling the thing out that's not parenthesized, right? If you have something, typically you have like something like c being the common factor, and then you have an equation, and then you have plus c and another part of the equation. Here, though, or expression rather, here the expression is the common factor, which leads to this kind of weird maneuver, but it makes sense after you see it, k plus 1. So we pulled out the k plus 1, and then we've got k plus 2, right? The k plus 2 comes from these two, and the k plus 1 comes from this. So we have k plus 1 times k plus 2 over 2. Now if we look over here, let's go ahead and simplify this out now. K plus 1 times k plus, and let's break those parentheses apart so that we can add those ones together. K plus 1 times k plus 2 over 2. And that's the same as what we have over here. So we proved that both sides are the same. So what we've done here is that we said if it works for some number, it's going to work for the next number. And we proved it worked for 1. So we now can say since it worked for 1, it worked for 2. If it worked for 2, it worked for 3. If it worked for 3, it's going to work for 4. And so on and so forth until we can't find, and for any arbitrary integer you want. So that's how we prove it. And so again, so that's the mathematical proof, okay? If on the other hand, though, that kind of like went over your head because you did not expect to do a bunch of math this morning, I totally understand. So we're going to look at squares, essentially. Come on. Is it because my hands are cold? Possibly? Okay. So let's see. Format background. Let's go ahead and make a grid. Can't really see that there, can you? No.
I think you're going to say the square one was the best one.
Yeah.
As you can see, you guys can see that, correct?
Yeah. So we're going to just do this as best we can. All right, so suppose I have this. I'm going to show you, like, again, t of 5, the triangular number for 5, and I'm just going to create a 5 by, and I'm just going to circle this 5 by 5 square over here, okay? As best I can. So if we're looking at the triangular number 5, we've got 1 plus 2 plus 3 plus 4, right? And then plus 5, right? You get the picture there. So I've covered 1 square, 2 squares, 3 squares, 4 squares, 5 squared. If we look at this and look at the amount of space that this has taken, and this is not a mathematical proof by any means. This is just kind of to help you intuitive it if the math did not help you intuit it. This 1 plus 2 plus 3 plus 4 all the way to some arbitrary number takes up half that n by n square. Or not just half. It takes up, if we draw a line, right, it takes up, if we draw a line through the center, it takes up a little more than half, right? A little more than half, right? What was the equation? The equation was n. So if the area, so wait, sorry, 1 second. The area of the square is n squared, right? A half that would be n squared divided by 2. This area that I shaded takes over a little more than half, which is n, and the equation we're using is n times n plus 1 over 2, which can be rewritten as n squared plus n over 2, which is a little more than half of the square, right? And as far as big O is concerned, a little more than half, right? A little more than half, it's around the same thing. It's still going to be this quadratic growth we're looking at, right? Or rather, quadratic growth like that, not like a little check mark. So there's your non-formal mathematical proof for induction there. But that is why, for problem 3, you're looking at the t of n gives you the big O of n squared. Now that means you can kind of intuit that 1 plus 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way to n squared. You know, that's going to equal something else. And since your initial intuition was n and n squared, your revised intuition is going to be correct, which is that if the other one was n squared, then this is going to be big O n cubed. And there's a formula, I don't know it off the top of my head, but I think it's something along the lines of n times n plus 1 times n minus 2 all over 6. I cannot remember the exact plus or minuses in there, but I do remember it's all over 6. But the entire point is that it is big O of n cubed, and you prove it the exact same way by proof by induction. So those are why those two are the same. And again, the reason I bring it up here is because this, this formulation, 5 plus 4 plus 3 plus, this formulation, doing 5 plus 4 plus 3 plus 2, is the most common way you will end up writing an n-squared algorithm, a quadratic algorithm, right? That is the most common way you will do it. And it's useful to know that that is O of n squared and not O of n. We will keep seeing it. Now again, over the course of this semester, for your final exam, you will need to know about 5 separate runtimes. For this exercise, obviously, I'm exposing you to some funky ones like O of n factorial, right? I'm exposing you to O of n factorial in this exercise. But for your exam, for this unit, you need to know 3 runtimes: O of n squared, and constant time, right? And again, on the exam, essentially, you'll be asked to basically evaluate an algorithm you just wrote, and that algorithm will be either O of n or O of n squared, because it's not going to be a constant time algorithm that you're going to be writing, right? It's either going to be something you go over once, or you go over everything in there multiple times. And because I said the scary word, exam, again, you don't really have to worry about the exam until, let's see. Let's look at this. So this is we're currently at the end of week 3. Week 4 is the 5th, 6th. So most likely our exam will be on the 19th, because you'll be doing it in lab. And I like to give my exam on week 6, so that's going to be February 19th. So you still have plenty of time. The focus of the exam will be linked lists and array lists. And I'm going to be awesomely nice to you right now and let you know, like every semester that I do this, this exam is like out of 100 points. And one of the questions worth 20 points on the exam is compare and contrast array list to linked list using big O notation. Okay, put this on the practice exam. It's on the exam. It's worth 20 points. And the way you'll be comparing them is using memory. Is basically how do they both use memory as an overhead? How do they differ in the runtimes for add and remove algorithms? And how do they differ in the runtime for get and set? I will be going over this in the practice exam. It's going to be on the practice exam. I will warn you about this question again, and I'll keep warning, and I'll warn every future semester about this, because until I get enough people where I said, oh, you all got it perfect, I think it's a great question to ask, because most people forget 1 or 2 things and end up getting like 16 out of 20. I highly recommend writing down your answer in advance and then putting it on your cheat sheet. You do get a cheat sheet, and then copying your answer onto the exam, because I told you in advance what it would be. Yes?
You said it's comparing array lists to linked lists using...
Big O notation. Using big O notation to compare and contrast them. It's easier to use that than, say, linear and quadratic, because you can just simply write a few characters rather than having to write quadratic.
Question?
Yeah. You said there's a practice exam. Will that practice exam cover essentially everything that's going to be on the actual exam?
Yes.
Okay.
In fact, what I do for the practice exam, my practice for practice exams, unintentional there, is that I make twice as many questions as I need for the actual exam, and then I divide it, and then I take half the questions and stuff them in the practice exam. And I typically use the harder questions on the practice exam.
Awesome. Thank you.
Also, when I do exams on paper like this, I typically have a 5-point extra credit buffer built in. So while it's 100 points, there are 105 points on the exam. So it's out of 100. And on the exam, there's a problem worth, I think, 5 extra. I think there's an extra credit point that's worth 5 points. And then there's 2 points of just kind of freebie points.
Now, another thing about this exam, too, is the fact that there are going to be some questions on there that you can actually kind of, like you said before, meta game, where if there's something that you don't quite, like, you know for a fact you can't just get in a specific thing, you can just take 5 points off just so that way you can submit something. Something's better than nothing.
Yep. One of the conditions is, for one of the problems is having your program run in O of n time. If you can't do that, just simply, accept the 5 points and move on, right? Better to answer your questions than to not. All right, so I've been talking for about 24 minutes apparently, so let's go ahead and get some demos done and help you out if you're stuck anywhere.
Okay. Just heads up, you guys